Hello everyone, welcome back to lecture series on computational fluid dynamics. Today we are going to begin with momentum equation. So we already completed continuity equation, and the second part of the governing equations will be momentum equations. So today we are going to continue with derivation of momentum equation in differential form. So let us start with list of assumptions. The first and foremost is flow is assumed to be continuous, and the phase of the flow is uniform, that is, it is going to be a single phase flow. So which ensures that the mass and the energy of the systems is constant. Then we assume flow is independent of viscous dissipations. Then electromagnetic forces are negligible, and vibrational forces and gravitational forces are considered to be negligible. These help us in reducing the complexity of equation. Complexity of the mathematical model. And we can strictly confine to most of the fluids which don't have the influence of electromagnetic forces and vibrational forces and gravitational forces. So we can confine ourselves to most of the fluids which we come across in routine cases. We can simulate flow over aerodynamic flow over bodies, maybe flow over airfoil, wing, which doesn't involve these kind of phenomena. Hence we can reduce our complexity of equation. Next, no chemical reactions. This also ensures that there is no change in energy and ensures equilibrium of energy in the system. So to begin with this derivation, let us consider the flow model. The flow model, what we are considering here is infinitesimal fluid element which is fixed in space. Infinitesimal fluid element which is fixed in space. So we are going to understand what is this infinitesimal fluid element, and the approach what we are going to consider is Eulerian approach, where we emphasize more on this particular element, what is happening inside this particular element. Based on that, we are trying to develop the equations. So let us try to understand what this infinitesimal fluid element is and how we represent various entities on this particular fluid element. So as you can see, this fluid element is generally a cubic structure or a cuboid having dimensions delta x in x direction. This is delta x, that is the width, and y axis representing delta y as total height of the element, and the depth of the element is considered to be delta z. So in the equation it is represented as dx, dy and dz. So I'll consider this as dx, dz and dy, where delta x is width of the element, delta y is height of the element, and delta z is the depth of the element. So if you observe this axis system, the root plane can be considered touching the axis or coordinate system of the model. So one of the important aspect of this particular approach is that we need to understand the representation of these planes and the parameters what we are going to consider. For example, we are considering here pressure P and tau, which is shear. So basically we are emphasizing only on these two because the force system is what is more important. Along with that, you can see there is need of density. of the model. So density, since it is a volumetric aspect, we are not considering that much, but since pressure and shear are the surface characteristics, we are going to emphasize more on representation of these surface characteristics. So if you observe, each of these parameters, whether it is P or whether it is tau, these are represented with the directions. So basically, P in x direction is represented by x, tau in x direction, and x equals to constant plane. So the representation of tau is very much important because it gives the direction and the plane on which it is acting. So if you observe tau has two components, y and x. The first part, y, indicates the plane on which it is acting, on which the shear is acting. And the second x represents the direction in which it is acting, in which shear is acting. So to represent this force system on this particular infinitesimal fluid element, we need to understand the notations what we are following. So if you see tau zx, so z will be the plane which is having z will be the plane which will be having z equals to constant, where the x indicates direction in which it is acting. So this is a representation of the infinitesimal element with pressure and shear. So P here can be represented px, considering it to be in the direction of px. Suppose if it is acting in y direction, for example, if your P is acting in this direction, so it has to be represented by py plus dou p by dou y. Then if it is on the bottom plane, it has to be py. So the plane where we are considering the coordinate system, that will be our reference plane, and on this plane all the parameters are initial parameters. All the parameters are going to be initial parameters. We can directly represent it with the representation with direct value, that is direct P for pressure and tau for shear, and x will be the direction in which that will be acting, x or y or z, which will represent the direction in which that is acting. And on the opposite surface or on the opposite plane, we are going to consider forces relative to the initial plane. For example, if you take the left side plane, which is, we are going to consider the left side plane. Since it is the reference plane, you can observe that tau xx is simply given without any variation, and P here I'll consider it as px. When it comes to the opposite plane, the same parameter will be can be represented with slight variation, that is dou p by dou x into dx. So the major assumption for considering this infinitesimal fluid element is that we assume the variations in parameters across surface to be linear. So when we consider approach to be infinitesimal element approach, we consider that the variations are always linear across the surface. So this is the primary consideration for infinitesimal fluid elements, and that is the reason when you look at this, the pressure at this surface will be indicated by P plus dou P by dou X into dx. This term represents linear variation. This term represents linear variation of pressure across the surface in x direction. So this is assumed to be total change in or pressure gradient in x direction into dx will get total change in pressure. And the same approach is considered for all the other planes, whether it is pressure or shear. So with this, let us move to the next part, which is the selection of governing models and governing law. So since we are considering infinitesimal element, let us consider the governing law. So the governing law on which the momentum equation is derived is law of conservation of linear momentum. So according to law of conservation of linear momentum, when two bodies are in motion, the linear momentum of the system remains constant unless acted upon by external force applied. So in an isolated system, the total linear moment of the system remains constant until unless an external force is applied. So based on the law of conservation of linear momentum, we are using Newton's second law for developing the physical relation between the various parameters of the flow. So Newton's second law states that rate of change of momentum is equals to force causing it, or force is equals to the rate of change of momentum of the body with respect to time. So we can rewrite that in mathematical form as F equals to d by dt of mv, where m into v, m represents mass of the system and v represents velocity of the object. So F equals to d by dt, that is time rate change of momentum. So this can be reduced into other form such as F equals to m dv by dt, or F equals to ma into m dot into v. There are various forms of this. Based on our criteria, based on our requirement, we can use any of these equations for developing the momentum equation. So the governing law is law of conservation of linear momentum, and physical relation what we are going to use to develop this equation is, or you can say physical model is law of Newton's second law of motion. Now let us enter into the derivation part. So before considering derivation, let us consider the forces acting on the control volume. So we can classify these forces into two types, body forces and surface forces. So as we all know, body forces are forces due to the mass and physical entities which are inside the body, and surface forces are considered to be the forces acting on the body, that is forces due to pressure and shear distribution. And since we have already neglected, there are some forces like nuclear forces, gravitational forces, vibrational forces. These kind of forces are neglected. So based on that, we can reduce all the forces to only these three forces. So coming to body forces, let us consider Fx, Fy and Fz to be body force per unit mass in x, y and z directions respectively. So since F, X, Fy, Fz are body force per unit mass, if I multiply them with mass of the system, then I will get the total body force. In that particular direction. So how can I calculate mass of the system? So mass of the system is nothing but density into volume. So what is density? Density is given by rho, and volume, for volume of cube or cuboid, it can be written as dx into dy into dz. Dx dy into dz. So the mass is equals to rho into dx dy dz, where dx into dy into dz is nothing but the volume of the infinitesimal element. So if I multiply this with f of fx, which give me body force in x direction, m into fx will be equals to body force in x direction. So let us write that. So total body force in x direction can be given by fx is equals to rho into dx into dy into dz is nothing but mass into fx is nothing but total body force in x direction. Similarly, we have to do it in other two directions, which is y and z directions. So we can write fy is equals to rho fy dx dy dz, and fz is equals to rho dx into dy into dz, rho into fz into dx dy and dz. So this is the expression for body forces in x, y and z directions. Now if we consider the second type of forces is surface forces. So let us continue with surface forces. In surface forces, let us consider pressure forces. Let Px be the pressure force in x direction, Py similarly in y direction, and Pz in z direction. So from the image, if you observe from the figure, this surface was having P and tau xx. The left side of the infinitesimal element on x equals to constant plane, that is yz plane. On the left hand side, P was the pressure. On the right hand side, it was given as P plus dou P by dou x into dx, and this will be multiplied by dy dz. Similarly, this is dy dz. So this is the pressure acting in positive x direction. This is the pressure in negative x direction. So we can resolve this as total pressure force Fpx, that is pressure force in x direction, is equals to, what is the pressure force here on left hand side and right hand side? On left hand side it is P dx dy, and the direction is positive x axis, so I keep it as positive, plus P plus dou P by dou x dx into dy dz is the pressure force on right hand side, and this is acting in the negative x direction, so I have to multiply with minus sign, so I can reduce this to minus. So P dx dy minus P plus dou P by dou x into dy dz. So if I can reduce this, I can rewrite this equation as dou P by dou x with a negative sign into dx dy and dz. So this is the net pressure force in x direction. So let us look at that. So in x direction we have considered this. So total force has to be Fpx is equals to dou P by dou x with a negative sign into dx dy and dz. Let it be equation 3. I'll just cancel this equation. This will be equation 3. Now let us consider shear forces. So unlike pressure, the shear was acting on 3 different planes. For example, if we consider this plane so this, it is tau xx plus dou tau xx into dy dz. Here it was on this particular plane, it was tau xx. Similarly on this particular plane it was tau yx. Here in this direction it was tau yx plus dou tau yx by dou y into dy dx dz. Tau yx into dx dz. So like this, each plane constitutes for one particular shear distribution. That is 1, 2, 3, 4, 5, 6 along with the components tangential to it. So we will be having total 9 components on 6 planes. 3 corresponding to shear in x direction on the direct plane and 6 on each surface. So we can reduce this or rewrite all the force system as tau xx plus dou tau xx by dou x into dx. If you observe, this is the tau xx, this is the term tau xx plus dou tau xx by dou x into dx minus tau xx, which is on this particular plane, it will be acting in the direction opposite, right, which is acting on dy dz plane, so it will be this value. Similarly, if you observe the bottom plane, this bottom plane will be having shear force as tau yx on the upper surface, as we have taken tau yx plus dou tau yx by dou y into dy, this is the plane. Similarly, on the front and backside plane of that, we'll have something like tau zx. On the front plane, it will be acting something like this: tau zx plus dou tau zx by dou z into dz, and the plane on which it is acting is dy into dx. So this is nothing but this term. So total tau in x direction can be written like this. So this equation can be reduced. This equation can be reduced to tau x is equals to, or tau x into, tau x is equals to, where tau x represents total force, shear force in x direction. So tau x equals to, we can cancel these two terms, cancel these two terms, cancel these two terms. So you are left out with dou tau xx by dou x into dx dy dz plus dou tau yx by dou y into dy into dx dz. Similarly, dou tau zx by dou z dz into dx dy. So when we sum up this equation, you can write tau as tau x is equals to dou tau xx by dou x plus dou tau yx by dou y plus dou tau zx by dou z into dx dy dz. So this is going to be the expression for shear force in x direction. Similarly, we can do it for y and z directions, where we can rewrite this equation in y and z direction forms. So hope you understood the expression for tau x. Similarly, if you want, you can write tau y is equals to dou tau xy by dou x plus dou tau yy by dou y plus dou tau zy by dou z into dx dy dz. Tau z can be written as dou tau xz by dou x plus dou tau yz by dou y plus dou tau zz by dou z into dx dy dz. So these are the three components of shear force in x, y and z directions. So that is about the shear force in three directions. So we have seen the forces, which includes body force, which is pressure, body force. Then we discussed about surface force, which is pressure, and now we are done with the shear force distribution. So from the Newton's second law, the LHS is done, which is force component. Force component we are done with the derivation part. Now let us consider the RHS part of the equation, which is rate of change of momentum. For that, let us consider infinitesimal element. Let's consider what is a mass. So this is the total force in x direction only. So this is x direction force component. which is represented by f of x. So this is nothing but fpx. This is tau x or tau x. All three components are represented by tau x, and this is the common factor, and this is the body force fbx, body force in x direction. So we have added all three components here. So total force in x direction is given by this. Similarly, you can write for y and z directions. Now let us consider the RHS part. So the RHS, we can consider rate of change of momentum. For that, let us first calculate mass of the system. We already discussed that mass equals to rho into volume, density into volume. Here volume is given by dx, dy and dz. Acceleration, F equals to ma, which is the equation we derived from, or we have rewritten the Newton's second law. F equals to ma, a is equals to d by dt of v or u, where v is the velocity. So here we are considering velocity as u, so du by dt. See, the u represents velocity component in x direction. U represents velocity component in x direction. Since we have derived expression only for one direction, that is x direction, the force component is considered only in x direction. So we are considering here velocity to be in x direction. The total velocity can be written as ui plus vj plus wk. So we are considering only x component of velocity. So a is equals to, you can write it as ax is equals to du by dt. So rate of change of momentum is nothing but m into a. So I have m, I have a, so I can write rate of change of momentum in x direction as rho du by dt into dx, dy and dz, which will be my RHS from the physical model. So now let us consider, let us equate both. So my LHS is fx is equals to minus p or minus dou p by dou x, I am considering as px, plus tau xx by dou tau xx by dou x plus dou tau yx by dou y plus dou tau zx by dou z into dx, dy, dz plus rho into fbx dx, dy, dz. This has to be fx. So rho into fx. So this is the force term what we derived. So pressure force, shear force and body force, and this should be equals to what? Mx, which is rho du by dt into dx, dy, dz. So if we can consider dx, dy, dz are common, so we can eliminate them. So I can write rho du by dt is equals to rho fx minus dou p by dou x plus dou tau xx by dou x plus dou tau yx by dou y plus dou tau zx by dou z. So this can be considered as the momentum equation in x direction. This can be considered as momentum equation in x direction. So similarly we can do it for y and z directions. Let's see what will be the final expression for that. Let me clear this. So you can try for the other two directions, which is y and z direction, where u will be replaced with v and fx will be replaced by fy, and dou p can be replaced, px will be replaced with py. So let us see the final expressions. For a total fluid flow, each direction should be consistent with the equation. So let us see that final equations in x, y and z direction. So in x direction, so rho dou u by, du by dt is equals to minus dou p by dou x plus dou tau xx by dou x, dou tau yx by dou y, dou tau zx by dou z into rho fx. Similarly in y and z direction, you can consider the equations. So these are the momentum equation in each direction, which we derived using infinitesimal element. Model. Now, if we consider body forces to be negligible, these all forces can be neglected. If body forces are 0, this can be body force equals to 0. If we consider flow is inviscid, then all the shear terms will be equated to 0. So you can rewrite for inviscid flow with no body forces, the equation can be written as rho du by dt is equals to minus dou p by dou x. So this is a reduced form of momentum equation when flow is inviscid and the body forces are 0. Similarly, you can write for rho dv by dt is equals to minus dou p y by dou y for y direction and similarly for z direction. So these are called reduced forms of momentum equation for inviscid flow with no body forces. So let's consider the overview of what we discussed today. So first we considered the assumptions for deriving this momentum equation, where we have considered flow to be continuous with single phase and neglecting various forces which may cause our equation complex or the derivation difficult, and we restricted ourselves to flow medium to be air. Now, after assuming we have considered the mathematical model and flow model we have considered to be infinitesimal fluid element, and the mathematical relation which we considered was Newton's second law. Based on Newton's second law, we have derived the equation. So in the derivation, we considered two forces, pressure distribution and shear distribution, and the third one was body force. So we have considered total three forces, pressure, shear and body forces, and we considered momentum on the other hand, and we have equated the forces to the rate of change of momentum, and based on this relation we have obtained these equations, and finally we reduced the equation to inviscid and flow with zero body forces. So that's it for today. Thank you for watching.